Right, welcome back to my electronics workshop. Now, I want to show you a pretty magic trick facilitated by a mathematician called Laplace. And what it's going to do is it's going to take calculus for us and turn it really into algebra. Now, there's nothing wrong with calculus. It just deals with differentials and integrals. It can be messy, it can be quite tricky to understand. Algebra is just moving things either side of an equal sign and so on, and is much more fundamental, which is why algebra is taught at second and third year of high school, whereas calculus usually saves itself for advanced levels in mathematics later on. Suffice to say that differentials and integrals aren't particularly friendly to work with when you're manipulating equations. Some people love it, some people find it really good fun, some people just can't latch onto it at all and find it very messy. So what we want is we want a shortcut. We want some little trick which allows us to manipulate complicated electronic circuits but without necessarily understanding the underlying principles of the calculus. And that's what Laplace does for us. Now, understanding the Laplace transform, you don't need to, you just use it. But what comes out at the end of it is almost magical, and it means that it opens a lot of doors for us. And this is exactly how simulators work. So the electronic simulator in Multisim is a clever box, a clever bunch of kit, but the bottom line is someone had to write the program which drives it. Well, how does it do that? How do you write a piece of software that can model any electronic circuit that you put in? Clearly that's not very well defined and needs some thought applied to it. But what I'm going to take you through here is just two representations of an inductor and a capacitor, or this is what it will lead to at the end. Two representations of an inductor and a capacitor that you can use in algebra rather than having to resort to calculus. But first of all, let's have a look at calculus. Let's have a look at the way in which calculus describes the capacitor that we saw in the previous videos. So calculus does this for a capacitor, or this is one of the equations which is used to describe a capacitor in calculus. So I of t, in other words the instantaneous current at time t, is equal to the capacitor times the rate of change of the voltage with respect to time. I equals c dv by dt. Magic starting block for anything to do with capacitors, voltage and current. And when you think about it, there isn't really much else that's left. We've got the capacitor, we've got current flowing through it, and we've got voltage being developed across it. That's a complete description of the operation of it. Okay, so if we want to get things in terms of voltage, you'll notice that voltage here is part of a differential, it's the rate of change of voltage. So what we can do is we can integrate both sides. So if we do that, we end up with the integral of I of t from 0 to infinity, although that's not particularly important for what we're talking about here, is equal to c v, and that's v of t. And all that means is that instant in time, that's all that really means. Okay, so what we can do is just simply rearrange this. So we've got c on this side, we take c to this side, it's 1 upon c. So we can say that v of t is equal to 1 upon c times the integral from 0 to infinity of I of t. Right, so it doesn't look like we've got very far on that, because all we've really done is rearrange the equation in terms of v of t rather than I of t. But that's okay, because this form here, I'll draw too many boxes around things, but this form here is the right form to take the Laplace transform of. Why do we want to take the Laplace transform? Take my word for it, a brilliant mathematician told us to. Okay, so what Laplace says, Laplace says that, forgetting all of this, I'm just going to have a function which is called g of t. It's any function, doesn't matter what it is, but it's not related to this at the moment. So I'm just calling it g of t. This is what Laplace tells us is the integral from 0 to t of some function of t, and you always have this dt, which just means with respect to time. And what Laplace says, and I'm not very good at drawing the Laplace symbol, but what Laplace says, the Laplace transform of this is just g of s is equal to 1 upon s f of s. So the f came from here. The 1 upon s is a representation inside, sorry, I didn't catch that was off screen. 1 upon s is the factor which has come from the Laplace transform itself, and all this capital G and lower g is saying is that this is in the frequency domain, and this is in the time domain. Okay, so that's what Laplace tells us that we can do with a formula which has this kind of function. Well, we have it here, look. So there's a great deal of similarity between this one here and this one here. The only difference is this one's got 1 upon c in front of it. Well, that doesn't make any difference, not really. And this one's got I of t here. Well, this one's got f of t, but they're just symbols. So you can imagine we can take the Laplace transform of that. So Laplace says, so let's put Laplace's stuff like this so that we don't get confused. So actually what we want to do now is we want to take the Laplace transform of this that we started off with at the top there. So v of t, it should be a lowercase v by the way, v of t becomes v of s because it's now in the Laplace domain, because we're taking the sort of pound note thing. We're taking the Laplace transform of this, so v of t becomes v of s. It's 1 upon s times whatever the function is. Well, the function here is I, so we have v of s is equal to 1 upon s times f of s, which in this case is not f, it's I. So we have I of s, and of course we mustn't forget that we've got a 1 upon c here, which isn't in here, but that 1 upon c, we can bring that across here. That's a bit messy, so we can just tidy that up a tad. And we end up with v of s equals 1 upon sc I of s. Remember, this is frequency domain. This is describing what happens in frequency. If we take the I across to the other side, we have v of s divided by I of s. Now what is that? What's v upon I? Just give you 10 seconds to think about that. What is v upon I? It's the impedance, right? So v of s upon I of s, or the impedance of a capacitor, because that's what we're talking about. Right at the start, we're talking about capacitors and their relation to current and voltage. So the impedance of the capacitance is just simply equal to 1 upon SC. So what that means is in any circuit, what I can do is I can take that capacitor and I can replace it with its equivalent resistance in the frequency domain, which is 1 upon SC. So everywhere I see a capacitor, I replace it with 1 upon SC, and then I can use it algebraically rather than having to replace every capacitor with some form or variant of this, which is going to be extremely difficult to manipulate because it has a differential and it'll have an integral sign contained in it. So it makes it difficult to manipulate. Now I've got something which isn't calculus, it's algebraic. Okay, I'll let you digest that for a while.